second morning popular interview question session. Today's questions, we will have 3 questions, so we will be really serious about our time management, and we will have 50 minutes.
Yeah, what's that?
50 minutes or 45 for each question.
Let's start with 45. I mean, depending on how much time we need the update. Yeah.
So this is the next version of the question we asked with Karam. And the question is, you are given an empty array of integers and every element appears 3 times except one. One element appears exactly once. And you have to find out what that number is. You can search the question from lead code. It's on the send the links. So example. No.
From the array is when the XOR all the numbers. The XOR of every single individual.
Yeah, like 2, 4, 3, 5.
Yeah. And then we can start from the left, go through the array until we reach 0. And we can say the number we are looking for is before that point because we reached 0. XORing every single number again.
What we get is the XOR of this.
If we start from left, guys, it's not a solution, just maybe it helps. So, I mean, if we XOR the whole array once, we will get XOR. How do you represent XOR? Like this? We get this value. Then when we start from the left of the array, we will get 0 when we come here. So we know that 4 is basically before that's for sure.
You updated the same file, right?
And when we start from the right again to XOR this value, basically
You created
we
this
stop
file.
here.
Or did you update the existing
Becomes
file?
0.
You created a new file.
So we know that 4 is between this number and this number. Maybe we can go from here to something. I have
The expected solution should be of 1 space complexity. In this case, what we do is, if we carefully look at each number's binary representation, actually we can find some kind of pattern. Let's right. If you see every bit, the 0 bit, the first bit and the second bit, in this case it is turned 6 times, which means 2 numbers have turned it on, that are the 3 and the 5. In this case, again 6 bits are turned on, which means where the duplicates are 3 times, so we have 2 numbers that turn it on. In this case, we have 4 bits, which means 1 number has turned it on. It appeared 3 times, but it appeared it is turned 4 times in minutes. 1 extra number turned it on 1 times. And if it was a duplicate number, it will turn it on 3 times. So the number of turned on bits will be of multiple of 3, right?
Yeah.
If we had, for example, 5 3 times, we would have 2 more 1s and 0s, and the turned on bits will be 6. In this case, we can find which bits the unique number turned on by getting its module. Right? We have no bit here. It is 0 because we have 6. Right? Yeah, 6 bits. This case 6 bits, but this one has 1 extra bit, and we know for sure that this bit is turned on by the unique number because we have 4 terned on bits, 3 is terned by the others. So we have 1, 0, 0.
Then, okay, so we can solve, for example, if every element appears 4 times, still this is a solution, right?
Yeah, it works for every.
Oh yes. Then duplicates are also doesn't have to be solved by XOR.
Yeah, this is another way.
Wouldn't this be n times log m being the m being the largest number?
Since we are given an integer, we may at most have 32 bits, and it would be order of 32n, which is basically 4n, and we don't need any more space. After looking at every bit, we will figure out if we have a terned on bit from the unique value or not, and according to the order, we can multiply this factor and we can get it. Is this clear?
Like since it's not log n of n, it's basically log n for the largest numbers value, log largest number value basically. That's why we can think of this as constant.
If you think you are done with binary manipulations, we can have a follow-up question. Yeah, okay.
I really didn't get the major concept of dynamic systems.
Okay. So we have, when we see the binary representations, let us carefully see the terned on bits, the ones only. In this case, we have 3 ones here and 6 ones. And if a number appears 3 times, if the bit value at that specific position is 1, it will be 1 3 times because it appears 3 times, right? If there is another number that turns on this specific position, it will again turn it on 3 times. So we will have a multiple of 3.
We will get the modulo of 3 basically, like how many times that bit was on. Like it's 6 here, right? 6 mod 3 is 0. Therefore, we know that the extra number has 0 in the corresponding bit. And once we look at the last bit, for example, that last bit, it is actually turned on 4 times, right? And once we get the 4's modulo of 3, it is 1. Meaning that bit is actually turned on by our extra number as well. Therefore, it has to be 1 for the number that we are looking for.
Got it?
For that, we have to convert it to binary first.
Actually, we can use the bit shifting this way for each number. That's why we are saying we need 32n.
Like basically, yes, you are kind of converting them to binary, but every time you consider 1 digit, you can look at mod 2 and then shift it to, actually shifting it right is gonna be more helpful in this case, I think. So basically, let's say we started with the first digits of the numbers, right? And in order to get the first digit, what you should do for a number? What's that? No, to get the first digit. If you shift right, the first digit is gonna be lost. Mod 2, right? If you get modulo of 2 of a number, you get the first digit, whether it is 0 or 1. So after you check this for the first digits, then if you shift all the numbers to the right by 1 and get the modulo 2, which digit are you going to get this time? The second one. And next time we shift it 1 more and then get the modulo 2, which digit are we going to get? Third one, right? So this way we can go over all the digits and basically decipher each digit 1 by 1 for the extra numbers we are looking for. Thank you very much, Anteneh. This was a very nice question.
I have a question.
Yes.
I'm not sure. When we start, if the binary is 1 1 and if another binary is 1 0 1, when we shift to the right, is it going to consider? Is it going to add the 0, right? It's going to add the 0.
So let me do actually execution on this input. So like we have first 2, right? What's mod 2 of 2? 0. And how about the second 2? It is 0. Third 0. Third 2, 0. And for 4 it is 0 as well. And then we have 1 1 1 1 1 1, right?
4 it is 0.
So this is the, what's that?
4 4. Is it 0?
So what's the first digit of Daniel? Again, you are going to get a great change for the Aldi.
I have that. I'm just saying.
How do we write 4 in binary?
1 0.
Is the first digit 0?
Oh.
We are getting just modulo of 2 for everything. At the beginning, we are getting modulo 2 for as it is. You know? Then, like, these are the numbers we get, right? How many ones did we see? 6. We get the modulo of 6 with 3. Then what is this? This is 0, right? It's divisible by 3. Therefore, the first digit has to be 0 for our extra number.
I thought you meant you start from the left.
No, we start from the right. Okay, so is the solution clear for everybody now? That's a very nice question. Like if you think of looking at things binary, I think the answer is gonna be visible immediately. But the trick is you might not be thinking binary, like thinking of numbers in the binary form, right? So this is a very good reminder of once we are dealing with numbers and we have to do things with constant space, let's just transform them into a different space, like binary space, for example. Then things can be easier. Thank you very much, Anteneh. This was a very nice question. You apply AND operation. What do you mean by AND operation? If you add all the digits, then it's gonna be 0 for sure.
A follow-up question. I think all of you think you are comfortable with binaries from now on, so to test it one more time, try this one. In this case, we are given a list, an empty, an array of numbers, and all elements appear twice, and 2 elements appear once.
And then they take the
And you are expected to find those 2
What
elements,
I'm doing this.
and the order doesn't matter.
Actually doing it the other way around. So I do it like this way.
For example, it can be
like if you're going to second digit one by one, so you get this two, and then I get the modulo of 2. It's the same thing. Yours works.
every element appears 2 times, and exactly 2 elements appear once, and return these 2 numbers. Now, I think we have 2 options of thinking in binary. The first one, the single number one. And since this one is a follow-up question, we have already 15 minutes.
Yes.
How close are you guys?
Not very close. Then let's give a hint. Let's give a hint. So once you XOR everything, what happens?
We got the result of 2 extra numbers.
Like basically it gives you the result of XOR of these 2 numbers, right? And like once you know that, let's say our numbers are here 1, 2, 1, 3, 1, 2, 1, 3, 2, 5. So basically once we XOR everything, we get the XOR of 3 and 1, right? And 3 is 3 and 5, 0, 1, 1, and then 5 is 1, 0, 1. And the XOR is 0, 1, 1. So, with this XOR, what if we XOR each of these numbers again with this? If I XOR 1, 1, 1, 1, 1, 0 with 5 again, what am I going to get? I'm going to get 3. If I XOR this with 2, what am I going to get? 6. Let's try. Like this is the XOR. Where is my XOR result? 110 is my XOR result, right? So 110. Let's XOR this with 110. Sorry, 2 is this, right? This is gonna be 0. This is gonna be 0, and this is gonna be 1. Sorry, this is 4. And for 3, if we XOR this with 3, what are we gonna get? I mean, 3 is gonna be cancelled, so it's gonna be 5. Right? And 110 is my XOR. If I XOR this with 1, I'm gonna get 7. So 4, 2, 110, 4. This is 4, we already done. So now I have each of these candidates. Can we go anywhere from this? Like we know that now it can be 532435172417. Okay. Can this information be useful? Maybe let's take 5 more minutes. Is there anything about these pairs that is interesting? So, for example, for the pairs, for the duplicate numbers, how many times do we see them? We see the same pairs 2 times, right? How about for the single numbers? In a different order. Can it be helpful?
Just cost of extra memory. That's why.
What is costing us extra memory?
To get this.
I mean, you're not gonna put them in set or anything, so.
Okay.
But like, what if again you apply an operation on them?
Okay. If you can get this kind of set of element, you can just construct both of them. For example, based on the index, we can get 117, 241, and 17. So you can subtract from the first element and the second element if you get that. This is
Okay, Anteneh, let's go to solution. Let's go.
In this case, our XORing all values would give us 6, right? And 6 is 1, 0, 1.
And 1, 1, 0.
Or 1, 1, 0. So the XOR of this results mean if we have a 1 here, it means one bit contributed 0 and the other contributed 1, or one number contributed 1 and the other way, right? Because only differences give us 1. So from this, what we can understand is some numbers at the first 1 bit, let's take this one for example, some numbers have 1 on this position and some numbers have 0. So let's group them. So those numbers who has 1 to the middle are 1, 2, and 3. Right? For this bit, for example. And for those, 1, 2, 3, and 2. Right? For the other numbers in which this position is standing off is 1,
7, 5,
and 5. So in this way we can understand that the duplicates fall in these 2 groups. Right? Because 1, 1, 0 means the result has come from something like 0, 1 at this position and other numbers having 1, 0 at this position. So we can group the numbers which has 0 at these positions in one pole and 1 at this position into the other. So in this way we can find numbers which contributed 0 for this bit and numbers which contributed 1 for this bit on the other group. So this gives us to single number 1 question. So the unique number falls in this and the other unique number falls in this group. So XORing all will give 3 and XORing all this will give 5.
Why does second group have 1?
Because these are those who contributed 0 for this bit to be 1. And these are the ones group.
Like basically we chose a bit which separates these two numbers, right? And after we separate them, we know that in each group there are even numbers of duplicate numbers and there is only one unique element. So XORing everything is going to result with that element. And do they have to differ in one bit? For sure, yes. Because otherwise they are going to be the equal numbers. Therefore the XOR needs to have at least one inside.
Okay, the second group is basically 0 at the second bit, right?
Yes.
Okay.
So let me repeat it once. Our result is 1, 1, 0. So we know that to find the XOR, for this bit to be 1, it means one side is 1 and the other is 0 and 1, or 1 and 0 only gives us 1. So the numbers contributed for this bit by contributing 0 or by contributing 1. So those numbers that contributed 1 for this bit to be 6 fall in one category and the others fall in the other category. And in each category we can find the unique numbers.
My question would be, is there a point to choose the second element?
For the XOR property, what we can deduce is from 0 it could be 0, 0 or 1, 1. Right? But 1 gives us a special property that is.
So we can choose the last also?
This one also gives us the same
Yes.
result, but
Okay.
we don't bother checking.
I think
the values.
choosing the last. I think choosing the last would be better.
Choosing the first one we find from the right.
And why is that? Why not just the one for the left?
It doesn't.
Doesn't matter.
I mean, there can be only one, so.
I mean, if we are traversing from this position, if we find the first one,
Okay.
we can just use that bit.
Maybe to clarify the problem, you should test it in 10 up to 30. Pick the numbers between these two ranges and make the top sum unique. Because
You have
Oh,
4
yeah.
digits, right?
4 bits.
4 bits, yeah.
So let's see that they are bit representation.
Use a different marker.
Okay.
Let's start.
So if we XOR all elements, what would we find?
I think we get 7, 1, 1.
One more unique element, like in the input. Oh, you have 14. There is 14 in the end. Can you? Yes.
If we XOR all elements here,
This would be 1, 0, 1.
0, 0, 1, 0, I think. Actually.
1, 2, 3. That's 1. No, the first one is 0. You can just count number of ones if it's even. Then 0.
It's
No, that's 0. I think like 6 ones. Yes.
So the XOR value is 2. So what we are grouping basically is those bits who have that has 1 in this position and those that are 0 in this position. So we have this, and this in the ones group, and this and this one in the zeros group. So the unique number separated into the zeros in the ones group. So this one.
We basically divide and conquer. When there are two unique numbers in the same set, we are not able to take the power of XOR much, right? Because like we basically get the XOR of two numbers. But that actually gives us a clue, because this way we can see in which digit these two numbers are different. And we basically divide all the numbers based on that digit so that the unique numbers, they go into separate sets. And we know that since the other numbers are they have duplicates, like they have, whichever set they go as pairs there. So they are going to cancel each other out. Therefore, by XORing everything in the corresponding set, we can reach to the one unique element. And on the other set, obviously, we reach to the other unique element too. So this way we can find them out. And like these problems usually, like I would say it's gonna be rare to have them in the interviews, because this is like a more two-step solution. So most of the interview problems, they are usually one-step solution. Meaning, like you see the solution and then you can go ahead and implement it. But here, like there are two things that you need to do. You do XOR first, and then you don't get to the result immediately. There is one more trick that you have to build on top of the first floor. In competitive programming, these things are very common. But in the interviews, they are not common. Thank you very much, Anteneh.
Do you have time for one last question?
Let's see. It's actually noon. Maybe after lunch we can do that, because if we start, we are going to be very late.
Yeah.
Cool. Thank you very much.
Awesome.